Okay, it's my great pleasure to introduce our next speaker, Yuan Su from Microsoft. Yuan will talk about optimal linear system algorithm quantum linear system algorithm with optimal QRS to initial state prep. Please join me to welcome our speaker.
Yeah, okay, thanks very much for the nice introduction, and very happy to speak at QIP. So the title of this talk is Quantum Linear System Algorithm with Optimal Queries to Initial State Preparation. Guang is the other author. Okay, so here's a definition of the problem. We have some coefficient matrix A. We have some target vector B as a quantum state, and we want to perform A inverse onto B. We want the normalized version of that. So there are some important parameters associated with this problem. So first, we have the so-called condition number. So it measures the non-singularity or invertibility of the matrix. And then we have the inverse success amplitude. So we have encountered a similar quantity in the previous talk. But here we have a similar situation because A inverse B is our desired vector. But we typically introduce a larger normalization factor. So the ratio between these quantities will give you the success amplitude. And of course, we have the accuracy, let's say quantified by the Euclidean distance. Okay, so you might want to ask, why do people ever want to care about this problem? Well, at least there are several reasons. Theoretically speaking, it could be an interesting problem on its own right. It just gives you a different perspective of describing quantum computation. More on the practical side, people encounter different kinds of linear systems in different areas of science. For example, in physics, maybe you want to compute many-body Green's functions, and it is also related to quantum linear system problem. And more recently, people have also discovered connections to other quantum algorithms, more advanced quantum algorithms. So for example, there are previous work on solving differential equations or performing eigenvalue processing or Jordan form processing on non-normal matrices. So all of these would use quantum linear system solvers as subroutines, and this will be the main motivation for this work. Okay, so with that, let's talk about the input model. So in this work, we assume block encoding access to the matrix. So block encoding is a common model that is used by many recent quantum algorithms. So it encompasses many other input models, such as linear combination of unitaries or sparse operators or other models. And for the initial state, we assume that we have a quantum operation that prepares that from some standard reference states. And then we can just count the number of queries to oracles OA and OB. So with this block encoding, there is a standard method to solve this problem by using the so-called QSVT. So we can perform some polynomial transformations, but to the singular values of the input matrix. This only produces a solution state with some success probability, as I just mentioned, but we can do amplitude amplification. So I wrote down the cost of this algorithm on the slides. For the initial state preparation, we'll have a cost contribution from the amplitude amplification. So that's 1/√P. But for the block encoding cost, we have two contributions, right? So we have one contribution from the amplitude amplification, but then we also have a contribution from the block encoding, from the QSVT. So we multiply them together, we get the total complexity. So this is just one example algorithm which we can use to solve the linear system problem. Here's a table which lists some other linear system solvers together with their primary innovations and as well as query complexities. So on the top of this list, we have the original seminal work of HHL, and the condition number scaling of that algorithm was improved by Ambanis using variable time amplitude amplification. And then the scaling with the accuracy parameter was exponentially improved by Charles, Kodary, and Soma using quantum walk combined with VTAA. And there are some subsequent more careful analysis of VTAA. But then there's a fundamentally different idea using adiabatic process to solve linear system. So the original algorithm, roughly speaking, has query complexity kappa over epsilon, but that was also subsequently improved. In particular, in 2022, there's an algorithm based on discrete time adiabatic theorem, which achieves kappa times log over epsilon. This is optimal scaling. The potential issue here is that adiabatic theorem is a mathematically involved result, so a rigorous analysis of that theorem could potentially give large constant prefactor in the query complexity. So, which is undesirable, but fortunately, just in last year, there's a new algorithm based on the so-called kernel reflection, which also achieves this optimal scaling, but the algorithm is very simple. Okay, so this is not the full story. Here I have an expanded table where I include contributions from both the initial state preparation and the cost to the block encoding. So here the HH algorithm is still staying on the top. It actually achieves optimal scaling for the initial state prep because we only have contribution from amplitude amplification. Of course, the cost to the block encoding is not optimal. In the worst case, it's kappa square. That can definitely be improved by the adiabatic approach. But on the other hand, it will have a worse scaling in the initial state prep. So until today, the only approach that simultaneously achieves nearly optimal scaling for both initial state prep and also block encoding is this method based on VTAA. So the state-of-the-art VTAA result is a logarithmic factor away from optimal, but this is under a strong assumption that the solution norm is known a priori. So if we don't know the solution norm, then the VTAA algorithm becomes more complicated. We need to use that to estimate the solution norm. And I have a complexity expression quoted on the top of the slides. It has additional overhead, and presumably the constant prefactor is also larger. So the main contribution of this work is twofold. So first, we develop a quantum linear system algorithm based on VTAA. And the complexity to that is 1 over square root p, strictly linear, in the inverse success amplitude for initial state prep. So the structure of this algorithm is simplified. It's based on deterministic amplification schedule, improved over previous constructions. So this is with solution norm estimation. If we don't have that, we can turn this VTAA into a solution norm estimation algorithm that is also linear in the inverse success amplitude with a lower bound replaced by that. Okay, so we also develop a block preconditioning technique that can boost up the success probability. When applied to the linear system problem itself, we get a second quantum linear system solver with optimal query complexity to the block encoding cost. So the algorithm is extremely simple. I can actually describe it in 2 sentences. I'll tell you that later. But for now, here's a list of some other applications to solving differential equations, to estimating or transforming eigenvalues of non-normal matrices, and to estimating ground state energy of non-Hermitian matrices with real spectrum. So this is more or less a summary of the main result and some basic setups. So in the following, I want to change to the technical stuff and give you some idea of what is going on behind all of this. Okay, so let's talk about VTAA. So here are some terminologies. First, we have something called a clock projection. So it's projecting onto the singular vector subspace with from some constant value down to some very small singular value. So let's say 1 over 3 to the j. And these projections are increasing. So at the beginning, you have nothing. But then you have larger and larger projections. And at the very end, you have the entire space. So, and then the second concept is called a flag projection. So it's projecting onto the undesired subspace of block encoding. So, and then we can combine them together. So for example, we can multiply pi j and pi b, and we take the complement of that. So what does that mean? Well, if pi j times pi b means at step j, we are getting the bad result. So the complement of that is at step j, we are either getting the good result or the result is inconclusive. So in other words, we are getting potentially good results. So these potentially good projections are monotonically decreasing. And next, we have the initial state. There's no problem with that. And then we have the pre-amplified algorithm. So in this case, we want to invert the singular values, but only within a small interval. And the cost of that will be 3 to the j, inversely proportional to the singular values. And finally, we can talk about amplitude amplification. There are different ways of describing that. For example, we can say, let's do R steps of amplitude amplification, or we can say, let's just keep doing the amplification until we are just above some threshold. Okay, so with all of these terminologies, I want to introduce you to this picture. So I am keeping track of all the potentially good probabilities. Let's start with the top right corner of this picture. So at the beginning, we have done nothing, so all the outcomes are potentially good. But as we perform more and more steps of quantum algorithms, the potentially good probability is decreasing. So we basically go down the stairs until at the very end, we are at the lowest level. And then in order to boost up the results, we have to do amplitude amplification. So we boost it all the way up. So this is a standard approach. VTAA is different. So in VTAA, we first perform one step of the algorithm. We immediately follow up with amplitude amplification and do a second step with amplitude amplification, and so on and so forth. So we have this kind of zigzag pattern, and we try to keep it on the top of this picture. Okay, so what is the complexity of both algorithms? Well, pictorially, you can think of the query complexity as the, for the standard approach, as the area of that red box over there, because we are doing all the algorithms and then followed up with amplitude amplification. So pictorially, the area of that giant rectangle will represent the query complexity of the standard approach. So for VTAA, we have some smaller boxes, blue boxes. There are many of these smaller blue boxes, and they are nested with each other. But the hope would be that maybe we can tune the sizes of these blue boxes so that when summing them up, the total area is still smaller than the big area on the top. So this will be the idea. And here's a more mathematical formulation of what I have just described. So we want to minimize the query complexity of VTAA. We introduce a tunable parameter that tunes the size of the blue boxes. There are some constraints that we have to satisfy. So for example, maybe we don't want to overcook the amplification, or maybe we want to control the loss factor. But in any case, this minimization problem has a closed form solution, depending on the P norm, or in some cases, quasi-norm. And we also have a table which compares this result with some previous descriptions. So in the middle, we have the original results from M-Binus. The complexity of that is 1 norm times square root m. M is the number of steps. By using triangle inequality, you can upper bound that by 2 norm times m. This is the most cited results. And we actually find that it's more convenient to use for the linear system problem. But theoretically, you can further lower the asymptotic scaling of the algorithm, and you can try to achieve 2/3 norm for the VTAA. Okay, so in this work, we use a suboptimal strategy for the linear system problem. But the benefit is that it gives us a deterministic amplification schedule. So to achieve the L2 norm scaling, we can choose the amplification threshold to be proportional to the potentially good probability times the cost function. So, but remember, the cost function is 3 to the j for the linear system. So this is nothing but a simple strategy where we just perform 3 steps of amplitude amplification and then do it until the end. There's nothing special about 3. You can also find some fancier choices like 9, 27, 81, or square root 3 or something like that. But all of them will lead to deterministic strategy. OK, so we have some further ideas on how to reduce the asymptotic scaling or the constant prefactor. Unfortunately, I don't have time to go into all the details, but I definitely encourage you to check out the technical version of the paper. OK, so this deterministic amplification schedule is depending on the availability of the solution norm. If we don't have the solution norm, then we can estimate that by turning the VTAA into a solution norm estimator. So again, this is a deterministic amplification schedule, so it's simplified over previous constructions. And the goal would be to get a constant relative accuracy for the solution norm. OK, so the second technique that we develop in this work is so-called block preconditioning. So the purpose here is we want to boost the success amplitude, right? So we want to boost this P success. So the basic idea here is that we find a projection that keeps the initial state invariant. So we have this projection pi times b is equal to pi times b is equal to b. So then what we can do is we insert a scaling operator in between the linear system, the coefficient matrix, and the initial state. So what does this scaling operator do? Well, this scaling operator S is shrinking the initial state. It's shrinking along the direction of pi. So the inverse of S is stretching along the direction of pi. This is the action of the scaling operator, but it does nothing to the solution state because it's a normalized state. So if we stretch on the numerator, if we do a stretching on the denominator, that will cancel out. So we still get the original solution state. But the benefit of this stretching is that we can significantly increase the success probability, thereby giving more efficient quantum linear system algorithms. Let me give you some ideas of how you can apply these results. So for example, you can define the stretching projection to be the ancilla state. This is just a trivial state, so you don't need any query to the oracle to implement that. So this is the case relevant for applications of linear systems to other areas, such as differential equations, eigenvalue processing, or ground state energy of non-Hermitian matrices. Alternatively, you can also define the stretching projection, to be the initial state itself. So this will consume some queries to the initial state. But the result is that we get an extremely simple quantum linear system algorithm with optimal block encoding cost. Here are two sentences. First, we block encode the scaling operator using some standard tricks. Second, we perform the inverse of the rescaled linear system using QSVT, and that's it. You get a constant success probability of the solution state. There are some caveats. Before running this time, we have to guarantee that the solution norm is estimated to a constant accuracy multiplicatively. And this can be achieved by adapting a reason technique to do a careful schedule of condition number. This is described in more detail in this kernel reflection paper. OK, so I think maybe it's time to give a brief summary. So in this work, we developed quantum linear system algorithms with optimal queries to the initial state preparation. So this is depending on the availability of the solution norm. If solution norm is not available, then we can turn the VTAA into a solution norm estimator that estimates the solution norm. The main technique is a more careful analysis of VTAA. And we show that for the linear system problem specifically, we can use a deterministic amplification schedule improved over previous constructions. And we also have a block preconditioning technique that boosts the success probability of quantum linear system algorithms. We apply these two techniques first to get a very simple quantum linear system solver with optimal block encoding cost. And we have applications to other problems, such as solving differential equations, estimating or transforming eigenvalues, or estimating the ground state energy of non-Hermitian matrices with real spectrum. Some future work directions. So it'll be very interesting to see whether we can further bring down the complexity to get the known complexity for both the initial state preparation and the block encoding costs simultaneously, or maybe there could be a stronger lower bound that take into account of both oracles. And also the quantum linear system solver based on block preconditioning technique is very simple. We expect that to be one of the most efficient quantum linear system solvers in practice, but currently we don't have a resource estimation result for that, so we'll be very happy to hear if you have some constant prefactor result for us. So thanks for listening.
Thank you very much for the wonderful talk. Let's take some questions. The next speaker, please come to the back of the podium to set things up. Questions, please. Is there?
Thanks for the very nice talk. And we kind of know that like a VTA is like a very difficult to cost. It's an extremely complicated procedure. So does your new analysis give us any like a new understanding of VTA, which maybe hopefully makes it like easier to understand, easier to analyze?
Yes, so I didn't have time to talk about this, but so the new algorithm for the linear system problem is based on deterministic amplification schedule. Here's I guess a pseudocode for the algorithm. So the idea is we have some parameter, pre-merging parameter, chosen depending on the solution norm, and this parameter is L in the pseudocode. So for step 1 up to m minus L, we just perform the original algorithm without any amplification, just perform QSVT. And then starting from the step m minus L, we perform 3 steps of amplitude amplification, followed by the algorithm, then alternate between these two. This is significantly simplified than the original previous constructions. We currently don't have a resource estimation result, but I agree it will be interesting to see any actual improvements in practice.
Do I understand correctly that Do I understand correctly that compared with the kernel reflection method, which you cite quite a bit here, the query complexity stays the same, correct? It's not an improvement to that.
The asymptotic query complexity is the same because that's the optimal scaling. Like I said, I haven't worked out the constant prefactor. That algorithm, our algorithm appears to be conceptually simpler than the algorithm, but like I said, I didn't work out the constant prefactor. Another point is that they are introducing some extra space. So they are not working on the original workspace. So they need to introduce some extra space to encode that kernel reflection. So in this work, we don't need that extra space. We don't need to embed the linear system in some larger space. So that could be a benefit.
Yeah, thanks for the very interesting talk. And yeah, I have a question on the VTA algorithm. So because like VTA is a very generic framework. So I was just wondering, like in your opinion, like other than solving linear system, is there like any other promising application where the tunable VTA can provide like further complexity improvement or something like that?
Yeah, so that's a very good question. So yeah, like I said, our understanding is that by tuning the threshold, you could potentially achieve this 2/3 quasi-norm. But currently, we don't know how to tightly bound that norm for any practical applications. And nor do we have any advantage of this 2/3 norm over like 1 norm or 2 norm. Yeah, I think it will be interesting to find maybe applications of this to other problems. So the caveat here is that to achieve this norm, we need to do amplitude estimations, just like in the original VTA. So it'll also be interesting to see whether we can bypass that additional overhead and directly utilize these new results.
Due to the time limit, we will not take another question. If you have further questions, please talk to the speaker during the break.